This is our second Spark session, so hopefully you will remember from Tuesday how this works. But a quick reminder, we are going to have 5 speakers today. It's going to be a challenge. 5 speakers. They are each going to have 15 minutes, and we have changed the timer. Last time it said 20, and so naturally, if you tell someone they have a 20-minute time, they use the 20 minutes. So today, they should hopefully stick to the 15 minutes so we can get through all 5 in the next hour and a half. If we do have the opportunity for questions and we're running to time, then again, I will try and field those. So do think about any questions you might have. And for our speakers, I think most of you have headsets. If you have a headset mic as a speaker, please feel free to stand anywhere. If you do not have a headset mic, please stand at the podium so we can hear you, and the clicker is on the podium for changing your slides. Okay, so our first speaker this morning. So my great pleasure to introduce Leslie Lamport, who received the Turing Award in 2013 for fundamental contributions to the theory and practice of distributed and concurrent systems. Leslie can often be seen at the HLF wearing T-shirts with maths jokes, though he did inform me that he left them all at home this year. But please do ask him about his T-shirts. And one of my favorite quotes from Leslie, when we did a video interview a couple of years ago, is I asked him, does he prefer tabs or spaces? To which he responded, tabs are evil. So today, he will be talking, or his talk is entitled, Coding is Not Programming. Leslie.
Thank you. Oh, this is set for 15. It's supposed to be set for 10. I'll try to be able to make the conversion in my head. I don't promise anything. Okay, coding is not programming. And I guess I have to go here because it's here. Oh, they changed it. Good. They're getting me all confused. Okay, coding is not programming. Coding is to programming as word processing is to writing. Can't write these days without word processing, but that's not exactly the most important part of writing. Programming consists of 3 things: deciding what the program should do, deciding how the program should do it, and implementing the how. And the implementing the how is the coding. And separate parts of the code may have to be programmed. Whenever you have a piece of code that's not trivial, it needs to be programmed. And programming has those 3 steps. An example, I'll give you an example. Computing the GCD of 2 numbers. GCD is the greatest common divisor. That's the largest number that divides both of them. That's what the program should do. Compute the GCD of m and n for 2 positive integers, m and n. And the how must be precise. I have to say positive integers, not just numbers, because it doesn't work on all numbers. And how the program should do it. Well, the how I'm going to use is Euclid's algorithm. An algorithm is an example of a how a program should do something. So how to describe Euclid's algorithm? I've told you the what. Now I'm going to tell you the how. Well, should I do it in a programming language? Well, if you look on the web, you'll see this book, Algorithms in Java. And to me, that makes as much sense as poetry in Microsoft Word. Programming languages are for writing code. That's why I like to call them coding languages, because there are other languages that people use when programming, and they don't generate code. They're not coding languages. I've written one of them. So here's Euclid's algorithm. First, I need to make a definition. For positive integers p and q, p mod q is the remainder when p is divided by q. So for example, 7 mod 3 equals 1, because when you divide 7 by 3, you get a 2 and then a remainder of 1. Okay, let x, here's the algorithm, let x equal the minimum of m and n, and let y equal the maximum of m and n. And now, as long as y mod x is not equal to 0, what you do is you set x to y mod x. and you set y to x. And then you repeat that as long as y mod x is not equal to 0. And when y mod x equals 0, and you exit the while, then the GCD equals x. How many of you have seen that algorithm? Okay. So here's the GCD of two numbers, 10 to the 99 to the 99 plus 10, and 10 to the 99 to the 99. Just two arbitrarily chosen numbers. So let x equal the minimum of those two, and that, of course, is 10 to the 99 to the 99. And y the maximum, it's y to 10 to the 99 to the 99 plus 10. And while y mod x is not equal to 0, well, y mod x, if you divide 10 to the 99 and 10 to the 99 plus 10, you get the remainder of 10, so it's equal to 10, not equal to 0. So you set x to y mod x, so x is set to 10. You set y to x, so y is set to the 10 to the 99 to 99. And you repeat. Now, y mod x, what is that equal to? It's equal to 0 because 10 divides 10 to the 99 to the 99 evenly. So the GCD of M and N equals x, which equals 10. So that's Euclid's algorithm working. Okay, couldn't we write Euclid's algorithm in Java? No, you can't. Euclid's algorithm can't compute that number because Java can't compute 10 to the 99 to the 99. I mean, if you work out the numbers, that's a lot more digits in that number than there are elementary particles in the universe. So Java can't compute it, but Euclid's algorithm computes it. So we can't write Euclid's algorithm in Java. We can only implement it for small numbers. Well, what if we only want to compute the GCD of small numbers? Could we then use Java? Well, we could do it, but we shouldn't. How the program should do it, it should be as simple as possible. And simplicity leads to fewer errors and better code that's easier to write. So Euclid's algorithm uses integers. Java can't use integers. Java, you can use 64-bit ints. And integers are simpler than 64-bit ints. You may think, oh, they're infinite, but integers, only have 2 to the 64 of them. But for example, for all integers, this simple equality holds. But it doesn't hold for 64-bit ints. You can figure out for yourself why. Java can use objects of class big integer. But integers are simpler than objects. Objects add all this complexity of the difference between equals and dot equals and all of that nonsense. So how should we describe them? Well, there's no one method that works best for all programs. Here is an approach that often works well, especially for multi-threaded distributed programs. And what you do is you describe an execution of the program as a sequence of states. So here's an example. In Euclid's algorithm, a state consists of the values of x and y. Why does Euclid's algorithm compute the GCD? Those of you who studied or learned Euclid's algorithm, raise your hand if you can tell us why Euclid's algorithm computes the GCD of these two numbers. Raise your hand if you can. I see 1, 2 hands from laureates. So a bunch of you were taught this algorithm that's supposed to compute the GCD, and you were never taught why it computes the G. Boy, education in computer science is really terrible. Well, is it because x and y were set to M and N? No, because the original values of M and N are soon forgotten. They're erased from x and y, and neither of them equals. You can't figure out M and N were by just looking at x and y. It must be because of something that's true in all states of the execution. And that something is this property, that the GCD of x and y at every step in the algorithm equals the GCD of M and N. That's So what the program does next depends on its current state, not what happened before. And a program always does the right thing because of something that's true of all states in all of its executions. And to understand why a program works, you have to know what that something is. And the something that's true of all states in all possible executions of a program is called the invariant. And your teachers who taught you Euclid's algorithm and did not teach you the invariant, they should be fired. Implementing the how, this is a recipe for writing better programs. These descriptions, describing, I said, those descriptions have to be written because, as a cartoonist Gwendon said, writing is nature's way of letting you know how sloppy your thinking is. And if you think, but don't write down what you're thinking, you only think you're thinking. So in what language? Don't be hung up by languages. Computer scientists tend to just be so concentrated on languages. Use whatever language works. It's not the language that's important, it's what the language is expressing that's important. I usually use English, sometimes with pseudocode to describe the how. And my pseudocode, that has integers. It doesn't have ints or objects. So your descriptions must be precise. But don't use coding languages. They're too complicated. There are tools for checking that the how satisfies the what. And to write those tools, you have to have a language. And some of them are required to use ints and objects. It's unfortunately true. Not the ones I invented, but there are some, and they're really useful. There's one language for describing things precisely that should guide you. It's a language that's been developed over 1,000 years, over thousands of years for stating things precisely. It's called mathematics. My Turing Award was for fundamental contributions to theory and practice. So this is not, I'm telling you, it is not just theory. It works in practice. Unfortunately, I don't have time to show you the evidence. So, thank you.
So as we decided to finish in 10 minutes, we do have the opportunity for one or two questions amongst the audience. So do we have anyone with a question for Leslie? Or is it still too early in the morning? Oh, no, we do. OK. I can see two. So let's go to the one at the back. If we can, there is a bright green fluffy box coming your way, which is also a microphone, to clarify.
Thanks for the talk. So my question is related to the fundamental algorithms that are being for the machine learning.
I'm sorry, could you repeat the question?
Yes, I was also struggling to hear that because of the reverb. Could you just repeat that question, please?
So the programs that are being written for the machine learning, how it is different from now as compared to the programs which were there in 1960s or 70s?
Okay, so
how are the programs written today differing from the ones in 1980?
Yes.
Well, programming language, coding languages have improved a lot since then. And, there's some very, nice programming coding languages. I've just been trained to say programming languages for too long. But they don't change the fundamental idea that you should write what the program is supposed to do and how it's supposed to do it before you write the code. I've been doing that. When I started programming in 1957, I didn't do it when I first started programming. And it took me a little while to figure this out. And when I write my little programs for my own personal use, what I always find is that thinking about what it needs to do, start out thinking something that looks like it's pretty complicated to code, But by spending a week or two thinking, not completely just in spare time, I will usually realize that I didn't need it to do exactly that. I can be satisfied with something that does something a little different, that's simpler, and I wind up with something simpler. And some other people who built a real system did that with using my language, and I don't have time to go into the details, but basically they said that that reduced the amount of code that they had to write by a factor of 10.
And then, Vint, did you have a question as well? Yep.
So this is a question about scaling. Some tasks that you want to program could be very, very big. And so I love what you're doing because it helps someone else who might have to maintain the code later to understand what you intended. But how do you manage large-scale programs with this method?
Scale is handled the same way scale is handled in engineering any place. Hierarchical decomposition. You start with, a very highly abstract view of what the system is going to do. And then you say how that's implemented. But that's a bunch of separate pieces. And then you recurse. Each of those pieces needs to be coded. And each of these pieces, you say what it's supposed to do. And what you should do, but in thinking about the high level, you should have shown that, or convinced yourself that, if each of the pieces does what they're supposed to do, then the high level one will do it too. It was just a thought that vanished. I'm sorry. Okay, go ahead.
Okay. Yes. Can we have a final round of applause for Leslie? Thank you very much. Okay, so our second speaker in this morning's Spark session is László Lovász, who was awarded the Abel Prize in 2021 for fundamental contributions to theoretical computer science and discrete mathematics. And in, as usual, my research ahead of this talk, I discovered that László is actually ranked 13th all-time in a list of IMO medalists with 3 gold and 1 silver, and is in fact the only IMO participant to receive prestigious international prizes in both mathematics and computer science. His talk this morning is entitled Discrete or Continuous: Two Worlds of Math. László.
Thank you very much. Discrete and continuous are 2 words in mathematics. They're 2 separate areas. If you think of the methods that are applied, if you have a continuous problem, differential equation, whatever, there are standard methods in analysis, derivatives, integrals, Fourier expansion, and so on. They're very deep, very well-established, very successful methods. In discrete mathematics, we also have methods. For example, induction, or counting, or random construction of a finite object. And these are also becoming more and more successful. So the methods are different, and so you think that there are really 2 mathematics. I mean, for some historical reason, we call them the same, but it's really 2. But it's not, luckily, this is not so. Oh, sorry. Okay. There are connections between the 2 areas. So first of all, it's a natural thing that once we are doing computing, we have to discretize everything, and so we approximate various objects, continuous objects like a smooth surface, by some discrete object like a collection of triangles which altogether approximate the surface. It is the other way around, you are also often approximating discrete objects by continuous objects. That's not so obvious, but here is an example. So there is a piece of steel. Is this a discrete or a continuous object? Now we know that it consists of a finite number of atoms. It's a network of a finite number of atoms, so it's a discrete object. But if an engineer has to determine what happens if the steel is a part of a bridge, then he doesn't go into analyzing all these atoms, writing up the equations that connect them and writing up this 10 to the 30 or how many equations. Instead, he thinks of it as a continuous object, and then you get simple, nice functions like density, pressure, temperature, and you can write up differential equations, and you can solve these differential equations, and the bridges stand. So this works. So you do this approximation both ways. Now, about a couple of decades ago, we began to think about making some more systematic connection between this discrete and continuous objects. And one of the things that we wanted that suppose that there is a sequence of finite graphs, finite networks, if you wish. And suppose that they are larger and larger, it's an infinite sequence, and as you go along, they become more and more similar. Trivial example there is if you look at complete graphs where any two nodes are connected, then there's not much difference between a complete graph on 1,000 nodes and a complete graph on 1,003 nodes. They are very similar, just everything is connected. Or if you look at grids, they are also becoming more and more similar, larger and larger pieces of grids. And there you can think of cycles and many other sequences of graphs where they really become more and more similar. That means less and less distinguishable by some well-defined statistics. So you have some set of tests, and if those tests are more and more difficult to distinguish them by those tests, then we want to call this a convergent sequence. And we worked out some, and other people, several people contributed to this kind of theory of what is the limit of this kind of graph sequence, and that kind of continuous objects appear in the limit. Now I would like to talk, however, about a more recent research, and I have to use a word here, two words which will probably be not so familiar for you as a graph or a differential equation, and that's matroids and submodularity. But every graph has a matroid associated with it, so it was inspired by the notion of convergent graph sequences. Matroids were introduced in the 1930s by Whitney and van der Waarden, called it abstract linear dependence. So you have a matrix there on the right, and you pick a subset of the columns, called the subset X, and then this forms a submatrix which has a certain rank. So that assigns a number to every such subset X that we call the rank of X. And the rank of X is called the rank function, and it has some trivial properties. Rank of the empty set is 0 and this sort of thing. But there is one non-trivial, which is this inequality, that the rank of the union plus the rank of the intersection is bounded above by the rank of one and the rank of the other. And this is a very powerful inequality, and that's why this theory of matroids became very successful in combinatorial optimization. It's really a central topic in areas, not only combinatorial optimization, also the theory of rigidity of structures and and many other areas of discrete mathematics. Now, I would like, however, so when I started to look at this problem and what is known about it, of course, if you want to go to the limit, then you will get infinite sets, and so you have to look at these submodular functions on infinite sets. And I began to look at the literature, whether it was ever considered, and then I came across a paper of Choquet from 1954, 160 pages long paper. In those days, it was even more outrageous than today, where he defined sort of an electric capacity of a set X, part of some big domain, and he proved that this electric capacity is, submodular, and he used this to show that it can be defined for all Borel subsets of X. That was the technical part of the paper. The point is, he introduced this electrical capacity, and it turned out that that's a submodular set function. Whereas, of course, the submodularity, I also mentioned there an example, but I'll obey Whitney and Rado, but the matrix example will be enough to tell you that in the discrete setting, the finite setting, there is also a very important notion. And now the question is, we started, so there was Choquet's paper, and it turned out that Choquet's paper, let me go back. So Choquet's paper started a whole line of research, the monographs, and it's an interesting theory. And of course, that is the discrete theory. And the surprising thing is that I could not find a single cross-reference between the two theories. So people worked either on that or on that, and there was no connection between the two. So, so that opened up a possible research area, try to find bridges. And we went on and indeed found bridges. Maybe my last slide here describes one of the bridges. In matroids, there is the greedy algorithm. That's well known for finding an optimum spanning tree. It's taught in many courses, so that you would like to find, it actually was designed by the Czech mathematician Borůvka in 1926. And it is simply that you can build up, say, a spanning tree by selecting edges one by one, so that you never create a cycle, and you always choose the cheapest one that doesn't create a cycle. That means it creates a new connection. And this algorithm gives the exact optimum, and it is a basic algorithm in matroid theory. It turns out that in the continuous setting, there is something, and I mean, it's a technical but very important theorem, which says that there is if you have a submodular set function on the Borel sets, but I just want to illustrate that there is such a theorem, that there is a charge, which is charge meaning a finitely additive measure. It's a terrible technical thing, and which is equal to the upper bound, which is less than or equal to this submodular function and equal to it on every beginning section. So that's sort of a continuous version of the greedy algorithm. As you move up with X, you always put as much into this measure as you can, as possible. Now, what is the morale of this? One of it is that really mathematics should be more concerned about understanding more basic ideas than just discrete and continuous. So making these connections that you really want to understand. So for example, here, greediness, the greedy is a greedy algorithm, is a notion which comes up on both sides and leads to fundamental results on both sides. And the other thing for me was that it is not easy because the language, the culture is somewhat different. And, with the sort of gray hair, I had to start learning measure theory in order to work out something. But so I think that you should always be open to learning new things, and in particular, sometimes go out and to an area, if you have the motivation to do that, you go out to an area which is maybe far from what you have worked until that point. Thank you.
We can probably squeeze in a question, actually. We've still got 2 minutes left on the timer. So do we have any questions for László? Yes, we have a question here. The microphone is on its way.
Thank you for the talk. When you talk about graph sequence, can this idea follow up to graph series? And maybe have partial sums to talk about their convergence?
Was that about the convergence of the sequence of graphs?
Graphs.
Yeah,
So
I
can
think
we...
he was referring to, you talked about the sequence of graphs, and he was interested in the convergence aspect.
Up to the series of graphs.
What were the theories? Series of graphs.
Series.
Oh, as in like what kind of graphs were they? Or
You mean series instead of sequence, or?
Yeah.
there you go.
I don't know. I was talking about a sequence of graphs, and it could be that it makes sense to sum up infinitely many graphs to form a sequence, but I don't know the meaning of that.
Anyone? Oh, we have one more question here. Let's just have, yes, microphone on its way.
Hi, this is more of a comment. In 1948, Alan Turing wrote a paper where he defines the condition number. And if you take the log of a condition of a problem that's continuous, that's a good way to translate continuous problems to discrete problems. It gives you the number of bits you need to solve a problem. So it's a related thing of translating continuous to discrete, and it really is due to Alan Turing. 1948. Very few people in computer science know about this paper, but it's a very interesting paper, and it's the genesis, really, of looking at this combination of discrete and continuous.
I will look at it. Thank you.
Okay.
Thank you.
Brilliant. Well, again, if we can thank you, László, for an excellent talk. Okay, so now this brings us to our third speaker, flying along. So our third speaker is David Patterson. David received the Turing Award in 2017 for pioneering a systematic quantitative approach to the design and evaluation of computer architectures. He also told me that he enjoys playing soccer and is just as happy when he plays well as when he has a research breakthrough. And possibly my favorite fact I have learned this week is on your 50th birthday, David bench pressed 325 pounds or 150 kilograms, which I think we can safely say makes you the strongest Turing Laureate of all time. However, if anyone in the audience would like to challenge this, I'm sure we could set something up. David's talk is entitled A Pragmatic View on the Impact of AI.
All right, great to be here. It's actually a follow-on to the last talk. I am also moving outside of my area of comfort to try something new. So I'll give you a little history of what's going on. In my past, I've done a couple of vision papers. Right around a little after the turn of the century, microprocessors switched from having one processor to multiple processors. They called it multi-core. And that was a big thing. And so I got a group of my colleagues together, senior faculty, younger faculty, grad students, to kind of write a vision paper, why this was happening, what are the upsides and downsides of it. And we wrote this long 55-page technical report, and it took off. It amazingly had 3,000 citations because people were interested in it, and people didn't write very many kind of vision papers of where things were headed. One of the former students said, well, that was a once-in-a-lifetime opportunity, it'll never happen again. Well, the next research project worked on cloud computing, similar confusion about what it meant, what were the opportunities, so we thought we'd write another paper, senior faculty, junior faculty, grad students, and this one had like 5 times as many citations. So one of the people in that paper, Andy Ponglinski, earlier this year came by and he said, I think it's time to write another vision paper. But this one about the impact of AI. He said, the discussions going on, I have these 2 extremes, AI doomers that think AI is just about to end humanity, and AI accelerists who think it's just about to change us all into the world of Star Trek where nobody needs a job anymore. So we assembled a group of people from academia, startups, and big tech companies, both some senior people like me and some rising stars in AI. And what our faith is that AI's outcome is not fixed. That if we do research, if we start programs, we can raise its upsides and lower its downsides. And we're not just aimed at the United States, but high, middle, and low-income stations. And what's different this time, instead of just people in our field, we're aimed also at policymakers and the public. So this is a stretch goal for us to see if we can do it. Our idea is to meet experts in a variety of fields, talk about the impact of AI. I'm just going to talk about employment today, given the impact, but we're looking at education, healthcare, and others. We're about 6 months into it, so if things work out in a couple of months, I hope you'll see this paper and people will be talking about it. If you start talking about artificial intelligence, this near-term one, another topic comes up is artificial general intelligence, AGI. So current artificial intelligence kind of works well in one lane, but if you leave that lane, it doesn't work so well. But AGI is supposed to be multi-talented. And this is a definition that's catching on. It's a highly autonomous system that outperforms humans at most economically valuable work. So it could do a lot of the things we do better than us. So many serious groups are working on it. We applaud that work, but we think the first step is probably, let's figure out the impact of near-term AI, and if we figure that out, that'll probably set the stage for this more advanced AGI that will come maybe soon, maybe for a while. The first thing that struck us is how geography affects the impact. Just in North America, if there's job displacement as a result of AI, it's hugely impactful for people. So in the US, having a healthcare is tied to having a job. In Canada, for example, it's tied to just being a citizen. Our unemployment in the US lasts about as half, so after about 6 months, if you don't have a job, you don't have any money. And the minimum wage is much lower in the United States than Canada. So Canada, the transition from job displacement will be a lot easier than the US. And if we look a little bit further down the border and look at Mexico and Honduras, in industrialized nations, we're worried about people like doctors and lawyers losing their jobs. But in these other countries, there's so few doctors and lawyers that there's no danger of that. What we need is a lot more doctors and lawyers. So AI could actually be this boon to the global south by supplying expertise that is missing, and maybe they would help the economy. So let's talk about employment. So as I learned is that kind of surprisingly, job creation and destruction happens all the time, leaving AI out of it. 2/3 of us today had jobs that did not exist in 1940. So in kind of one human lifetime, the job is completely changed over. I looked at census data in the United States from 1970 to 50 years later. And in 1970, the most popular job of these 4 jobs was typists, and then it was telephone operators, and then lawyers, and at the bottom was programmers. As we fast forward 50 years later, those roles reverse. The US population went up about 1.6, but there's 4 times as many lawyers and 11 times as many programmers. So healthy economy relies on worker productivity improving. It has for a long time. And especially looking forward, most of the industrialized nations are facing a declining population. The number of people who are going to be 30 years old, 30 years from now, are already born, right? So we're going to have to improve productivity if we want to maintain our lifestyles and let people be able to retire. And AI could be a boon for that. And now, the impact on jobs actually depends on what economists refer to as elasticity of demand. If it's inelastic, then productivity gains are going to mean fewer jobs. And in the US, a great example of that is agriculture. Amazingly, in 1900, 40% of everybody's jobs in the United States was in agriculture. 40 years later, that was 20%. 30 years after that, it was 4%. And today, it's 2%. So if we improve the productivity, it'll just mean that there's probably fewer people working in agriculture. If it's elastic, then actually improving the productivity will actually increase jobs. So I already gave you an example about programmers. Programmers, guarantee you programmers in 1970 are not as productive. Some of us in the room remember what programming was like in 1970. Punch cards, Fortran. It was bad old days. But we have 11 times more programmers. Even commercial airline pilots, jet engines are huge improvement in productivity, but we have 8 times more pilots today than we had in 2020. So does AI actually help employability? Well, what we've noticed is if AI concentrates on human augmentation, that has much more positive benefits to society than on human replacement. Because human augmentation actually increases a person's economic value, increases their employability. So that's a positive if we do augmentation. And some of the benefits of augmentation are the person can act as a safeguard in case AI veers off course to avoid like the hallucination problems that happen with LLMs. And then people and AI can make different mistakes, and so the combination can make them more successful. So, and then some specific examples of small case studies, like how much does AI really help or not? And there's a few studies. The first one is the Harvard Business School. And they looked at consultants, and what they found was actually the lower skilled consultants got much more benefit from AI than the high skilled. In fact, the low skilled ones plus AI outperformed the high skilled ones. The University of Minnesota Law School looked at young attorneys, and they found on average they went about 25% faster with AI. MIT did a study about writing, and it was almost a 50% speed up by using AI. And Microsoft for programming or coding, tasks went up by more than 50%. So there seems to be evidence of that this really is helpful. And there's going to be a U.S. National Economies has been working on something called AI and the Future of Work. This should be a very important report. It should come out within the next couple of weeks, which will provide more information. So the conclusion here is that if we can direct research in AI towards gains in doing augmentation in elastic fields, we'll have this very positive benefit that's going on. And if we can partner with policymakers to encourage that behavior, we can, things could turn out a lot better than people fear. And one of the economists we talked to says, now we're not trying to predict what is going to happen, we're talking about what could happen if we do the work. He thinks it's possible we could rebuild the middle class in high-income nations. That could be a positive if we policymakers and practitioners try and aim for improving that. And we could actually make expertise more widely available in the low and middle incomes who desperately need it. Okay, with that, I think I am ready for questions.
Thank you, David. And I'm sure there will be many. There are already hands up. Okay, let's go to this person near the front first.
So my question is, in your understanding of AI and employment, did you also look at how it will impact migration of population and labor, like like how people move for job, like how that will be impacted when AI for employment comes into picture?
No, I don't think we talked about, you mean moving from different countries?
Yeah, different countries, different cities,
Yeah.
and how it impacts the economics.
We didn't really address that. I mean, if we're going to have a shortage of, if the high-income nations have a shortage of workers, one solution would be to immigrate more people. But that, in today's politics, immigration is a very contentious issue. So I'd be surprised if that's the solution. I think it'll be easier in many countries to improve productivity, which AI can help.
Yes, yeah,
Well,
go to the front. Yeah.
Thank you for the really great talk. I was just wondering if you're familiar with Tyna's work, the GPTs are GPTs.
The what?
GPTs are GPTs, an early look at the labor market impact potential on large language models. She's at OpenAI now, but she's done some work with the policy team on the labor market.
No, but if you could send me a paper, I'd be happy.
Awesome, thank you.
There's a lot of papers in this area, but happy to read it. Okay.
Yes, if we can go. There's a hand over there. Yeah.
Thank you so much for the presentation. I want to pick my question from two statements I was able to write down from your presentation. You spoke about industrialized countries having reduced population. And at the same time, you spoke about
having what?
Reduced population.
Reduced population.
Reduced population, yeah, okay.
Yeah. Then also, you're talking about artificial intelligence complementing us instead of replacing us. So, and I read a couple of papers that gave reason for why industrialized countries have reduced population. So, do you think if AI is able to complement us, it might lead to increased population in industrialized countries?
So could the impact of AI and the things you've discussed lead to the population increasing in industrialized countries?
I like that idea. Well, I guess I would be surprised about that. I think the population is declining, I think, because people choosing not to have children, because it's, maybe if the return of the middle class made it more affordable to have children, maybe that would lead to greater children, but it's not obvious to me that would happen.
Okay, and then I think we've got one final question there.
Thank you for the talk. I just wanted to ask about the observation you made, which was the field of programming is an elastic field, and so the claim is that by introducing AI, you could increase job market there. Is there any worry about then in the inelastic fields like agriculture, you would be pulling away people from that, and then therefore a vital part of the US economy or any other economy like agriculture or other inelastic fields would suffer in return?
But yeah, I think what was interesting to me in learning about this was, I think when people talk about AI, there's kind of a general fear that everybody's going to lose their job, or that vast numbers of people's jobs, or they'll become part-time workers. And so it was helpful to get this view, well, it kind of depends what fields we're talking about. There is going to be disruption. I mean, I would encourage my AI colleagues to focus on augmentation in elastic fields, but that's not going to limit it to that. I'm sure there will be efforts that will go to inelastic fields that will lead to job disruption. I think that's likely to happen. And so I think as a society, we better prepare for that. We better prepare that there's going to be disruption for some people in some fields, and to help them move into fields where there's greater growth. I don't think it's likely. I don't think if you have a job right now that you're happy with, that you're going to abandon that job to move to these other fields because it's such a high overhead to do the transition. I don't think that's likely to happen. I'm more worried about what's going to happen to people who want to keep their jobs where the productivity means that they no longer have that opportunity. All right, I think my time's up.
Yes.
Thanks very much.
David, thank you. Okay, so our next speaker, fourth one of the session, is Reddy. Raj was awarded or received the Turing Award in 1994 for pioneering the design and construction of large-scale artificial intelligence systems. And during my research, I discovered he is a member of the US Academy of Engineering, the Indian Academy of Engineering, and the Chinese Academy of Engineering all at the same time. And this is alongside the 13 honorary doctorates he has received, which at 6 years each would give 78 years, which is a literal lifetime of research. Raj's talk is titled The Promise and Perils of AI. Raj.
Good morning. It's always a pleasure to follow or listen to Dave Patterson. I've known him for over 40 years, and I always learn something new. And today's talk by him was exciting for me because I didn't know about the effort. But my personal views are completely complementary to what he said. But the main difference will be, I will not talk about dystopian future, where the world will be taken over by robots and all of us will become slaves. I don't think it'll happen. And even if it's likely to happen, it won't happen in the next 1,000 years. That's my prediction, okay? So we talk about AGI, artificial general intelligence, and John McCarthy, my advisor, had a very interesting quotation. This comes from about the 1970s. He said, to reach human-level intelligence, we need 1.7 Einsteins, 3 Maxwells, and 0.7 Manhattan Project in funding. I don't believe we have any of those at this point. No one is spending that kind of money, and more importantly, having worked in this field since 1963, none of us have ever talked about replacing humans. We only talked about augmenting or enhancing the human capabilities. So the first slide is basically, we need to start with a clear definition of what we mean by AI. And I have my definition, which is, I created this in 1965 when we were talking about what is computer science, what is it? And my view is the role of computers and computer science and AI is to enhance the human capabilities and mental capabilities. Just like engineering is a field which enhances our physical capabilities, we can cross bridges, we can cross oceans, we can fly on all of that. Anything that we use with our mind, our brain, it'll be possible to enhance the capabilities of that activity so that we can do things faster, better, cheaper. That's all the definition of AI is. AI is an intelligence amplifier. And anything else of replacing humans and so on is beyond the scope of my definition. And none of us, at least working in the field in the 60s and 70s, ever talked about replacing humans because they were so far away. And whether it could happen today, it could, but it will require 0.7 Manhattan projects of a huge amount of funding to kind of create an artifact that will replace it. So here is an interesting commonality with Dave Patterson, namely, if you could do whatever you're doing, let us say AI is only going to enhance your productivity. If you could do everything you do in a day in 1 hour, what would that mean to society? What would that mean to us? And so the broad perspective of that is, if we can enhance our productivity by a factor of 10, that means all of us can do 10 times more work in a day or a year that we would now do. That means we can either take, every work for 1 day and take off 6 days, or we can produce more because there are a lot of people that need more. There are a lot of people with unsatisfied needs at this point. We need to create more wealth. So one hypothesis is by 2040 or so, we will have a GDP, global GDP of $1,000 trillion. Today it's about $100 trillion. So if you have a $1,000 trillion GDP, what would that mean? Okay. So what I'll now like to do is kind of go through what I think will be possible, not might be, will be possible in the next near-term future, and how that will impact society and help society, and what are all the problems we have to solve in the same near-term future. Next slide, please. So next slide, please. So the main hope here is it will help the people at the bottom of the pyramid. About 30 to 40% of the people are not benefiting from our technology, and at this point, in the future, I think they will be impacted. How will that be? How will they be impacted? Next slide, please. So I already talked about this. I think clearly with appropriate actions, we will be able to eliminate lockdowns, which cause serious disruption to society. Next slide, please. And it will also make it empower people at the bottom of the pyramid. Next slide, please. This leads to how will it help the people at the bottom of the pyramid? These are all, these require what I call intelligent assistance to help people that cannot read or write. And that requires a line of research that we are not yet completely working on, what I call guardian angels and cognition amplifiers. A cognition amplifier is something that will do things that you already know how to do, faster, better, cheaper. Guardian angels will do things that you don't know how to do. They can figure out things that are going to happen on your behalf and help you to do them better. Okay. Next slide, please. So, first thing that will happen is elimination of the literacy divide. There are about 1.5 billion people in the world that can't read or write any language. And I think using our technology, they will be able to overcome that. If you're kind of curious about how this might happen, there is a whole research that has happened called Learning X Prize. I recommend that you go look at it. And the main challenge there was, if you gave a tablet to a 6-year-old who did not know how to read or write or anything, there's no teacher, nothing else, can they learn how to read and write and do arithmetic at the first grade level in a year or so? And I thought that was going to be very difficult. It was difficult, but two groups got the $10 million prize. And I think it's an exciting thing, and that's exactly what I'm hoping is needed for everybody who can't read or write. And so the next slide, please. The next thing that has been solved and will be solved is what I call language divide. And here, I predict that we will be able to talk to each other. I can be talking in Telugu, and you can be talking in Marathi, and both of us will be able to have a routine conversation. And I leave it to you to figure it out. I'm sure you're all very smart. If I had a phone in my pocket listening to what I'm saying and doing speech recognition and translation, and same from the other side, and so we could be talking. It will be, you know. So, next slide, please. Okay, so we could spend a lot of time, given our limitation of time. Next slide, please. First thing is job losses. You know, Dave Patterson talked about it, and I agree with him, everything he said, except the near-term disruptions. It turns out, while in the long run, there will be no unemployment created by AI or any technology, in the near term, even right now as we speak, a lot of people have been laid off in programming fields, in Google, AI, Microsoft, and they can't find another job. They're looking around. So what we need is a societal solution for near-term disruptions. They occur not just because of AI or technology, they occurred when we created NAFTA. And many of the jobs went to Mexico and some to Canada, and people in Johnstown lost all their jobs. And that's why we elected Trump. They were all completely unhappy with the Democratic policies. We need to figure out how to deal with localized disruptions that will, in fact, impact the thing. One solution, again, it's a pipe dream, perhaps, is UBI, Universal Basic Income. Everybody gets living wage, whether they're working or not. And then the question is, how will society figure out how to pay it? And there is a whole theory called modern economic theory, where it says you can print as much money as you want, don't worry about deficits, because as long as you do not increase inflation, you can print money. And that key word is inflation. If we create a lot of money, and they're all buying things that are become scarce, then you have inflation. However, if there's a lot, 10 times more productive society, why aren't we using them to produce products that people want for buying those things? So if you haven't looked at modern economic theory about printing money without any, I recommend that you look at it. So I think job losses is going to be, already there, they will continue to be, and ultimately it'll stabilize. But temporarily there'll be serious disruptions and serious impacted families, and we need to say, how are we going to help them? Unemployment insurance, which pays you 10% of your wage, is not good enough. We need to have an unemployment insurance that pays the same wage for at least 3, 4, 5 years while the society stabilizes into a new equilibrium. Next slide. Self-driving cars. So it turns out we literally stopped inserting autonomous cars into society because there's an occasional death. But did you know that human drivers kill or are caused to be killed 1 million people in the world? In the US last year, is about 45,000 deaths. And more importantly, the economic impact of these accidents is about $55 billion in the USA, which could be reduced by a factor of 80% if we had intelligent accident avoiding cruise controls. So my recommendation is we should go whole hog on self-driving cars. Not that we should simply still have a driver, but most of the time human beings make mistakes, and we need to kind of have somebody else kind of protecting us from ourselves So if I were the czar, I would require every car that is produced have self-driving capability. And so if I'm doing something stupid, it can take over. Even otherwise, we could benefit from having self-driving cars. Next slide, please. This is the most serious one, malicious deepfakes. And I think the only way we are going to deal with this is to have severe punishment for anyone that indulges in that. It's okay to have a satire deepfake, and even that should be clearly labeled, but malicious deepfakes or political deepfakes should be legally punishable. And here is next slide, please. I've run out of time. Killer weapons. Again, we are barking up the wrong tree. We should not be thinking about killer weapons being produced by AI, but we should require all countries to produce humane weapons. There's no reason in this day and age where they should be hitting a hospital or a school. We can build weapons which will do intelligent targeting to the soldiers. Even the soldiers, they're all pure, if you take a random soldier, of an enemy soldier, they are not your enemy. They're just a random guy that has been picked out of the street and fighting. Why should he be killed? We can kind of make weapons that disable people rather than destroy people. Okay. I think this is the way we should be thinking in terms of what AI should do and could do, not what it might do. Next slide, please. Next slide. We're done. Okay. There are lots of other hazards. Next slide. So in conclusion, AI will have profound impact on humanity, but not only increasing productivity, but creating tools like for people at the bottom of the pyramid who cannot read or write and speak your language. But we have a lot of legal, social, governmental mechanisms to control serious societal problems. Thank you.
We can probably do one quick question, if there happens. Oh, that was a very quick hand right there. I didn't even finish mentioning it. So yes, this person in the center aisle, yes, we can get a microphone over there.
Yeah, thank you so much. A quick question for the legal approach. How would that work in the international world? I mean, you said you are in favor of legislation against deep fakes, but if that's a state actor from another country, I mean, would they care about what's legal or not if they wanted to meddle in the US elections or so? Thank you.
Yes, so it was a question about the legal aspect. So if you make something illegal in one country with like the deep fakes and the fake stories, why would another country care about that?
Yeah. So, we have such a thing as chemical weapons ban treaty. All the countries, it's an accepted thing. And how did that come about? I did some research on it. It came about because all the countries came together and said, this is not the right thing to do. And they agreed not to produce them. And most of the time, most of the nations have agreed to it. Occasionally, there was been a Saddam Hussein kind of person who would use chemical weapons against Kurds. But normally, and they have faced sanctions. So we need to work on societal mechanisms. And the way I say it is, even if you take simple things like a driver's license, in 1920, there was no driver's license. People were driving around and killing people and having accidents. And finally, society said, we must give everybody a driver's license. You cannot drive a car without a license. In the future, we will need health license. If you want to move around in the age of pandemics, you need to have a green passport, which is your watch, which tells you whether you're infected or not, right? So I think these will emerge. And the society will work out solutions to these problems. And there is nothing for us to be worried about saying they're going to take over the world. It's like getting in a plane and saying, "Mate, what if the plane crashes, so I'm not going to get on the plane? Or what if there's an asteroid hits the city?" And these are kind of millions of year-like events, some of them, not airplane crashing. And I think the society will evolve to do the right thing. And I think what Dave Patterson's group is doing is exactly what we need, some long-term policy thinking. Thank you.
Thank you very much, Raj. Okay, so this brings you to our final speaker. We started with a Leslie, and we have gone full circle, and we are going to end with a Leslie. So our final speaker is Leslie Valiant, who was awarded the Nevanlinna Prize in 1986 for contributing in a decisive way to the growth of many branches of computer science, and then received the Turing Award in 2010 for transformative contributions to the theory of computation. When I emailed Leslie ahead of this talk to ask about his hobbies, he replied, "I enjoy talking last and finishing on time." So, Leslie, the challenge is yours. His talk is entitled Educability, a Model of Human Cognition.
Okay, well, thank you. So this talk has relationships with the previous talks this morning, but does take a different take. Oops. Okay. So basically, it's about a definition, which is called educability. It's a definition of capability, which I believe humans have, and it's named to remind one of the main phenomenon it's similar to, which is our capability to be educated. So in some sense, the one-sentence summary is that it's to be contrasted with the notion of intelligence, which we've used for a long time, but there's no agreed definition of. So I'm interested in a term which describes human capabilities, which one can define, and intelligence has been pursued for a long time, and we cannot define it. And in fact, I don't think that the term intelligence has been that useful in itself in getting us where we are in AI. So this is primarily about us humans, a description of us humans, but inevitably, since we make our machines to resemble us, we're not very imaginative. It also has something to do with AI, and hopefully it's a contribution to the discussion of AI. So, for example, we talk about general AI, when in fact we don't quite know what I is yet. Okay, so to say something about humans and to stay safe, it's important to stick to something which we believe is a natural phenomenon. And the natural phenomenon I'm looking at will be cognitive capabilities of humans, and it would be too much to consider everything we do, result of a billion years of evolution, but we can narrow it down a little bit and focus on just the difference between us and our immediate predecessors, and that was a more finite piece of evolution. And so let's define this notion of a civilization enabler, which is a cognitive capability which accounts for our success in having created the civilization we have. So this is a cognitive capability. And my hypothesis is that this capability is this something I can define, educability, which captures the main aspects of it, and I'll spend a few minutes describing that. So there's a book on this, and the cover designer did this. I've forgotten the title and the author. And what this suggests is that humans have gone from an arrowhead to a cursor on a screen in a small amount of time, in an amount of time where clearly there's been no biological change in our species. And the question is, what capability do we have which enabled us to go in a fairly short period from one to the other? So, how do you answer a big scientific question? Any clues? Well, we may not have Newton's and Maxwell's around, but we can try to learn from them. And so Newton had 3 laws. Maxwell had 4 equations. And so they had theories with multiple components, each expressed quite precisely in terms of mathematics. And in their cases, a single component would not have worked. And certainly a vaguely defined notions would not have worked either. Okay, so educability is defined in the spirit. It's got 3 aspects, which I call pillars, and each one is defined quite precisely as a model of computation. Okay, so this general subject area, of course, has been researched for a long time. So the differences between humans and even our closest relatives has been studied in hundreds of aspects, and people have speculated on in what sense we're different. So I'm a bit specialized here. I'm interested in the cognitive capability rather than all the other differences we have. So this is the civilization enabler. And of course, many academic communities have suggested answers to these questions. And in what way humans are special. So eyebrows may be unique to humans, but it's not a cognitive capability. Lots of people emphasize social learning. Intelligence, main problem is we can't define it as a behavioral notion. You know, there's no definition of how you recognize an intelligent person, for example. So we need something else. So actually, what did Darwin think? Darwin thought that most of these simple standard notions you find in the dictionary, A, they're vague, and B, humans aren't unique in any of them. So he thought in all these dimensions, it's all a question of degree. That each of these notions, other species has as well to some extent. So it's frustrating to answer this question. But I think the advantage we have now over Darwin is that we're advanced in some sciences, and in particular, so I will use computer science, models of computation, which is a mathematical way of expressing functional capabilities. And so the main advantage we have now, over 150 years ago, is that we can express slightly more complicated notions. We should keep things as simple as possible, but at least we can express things which they wouldn't have known how to write down. So things aren't so hopeless. Okay, so I'll just tell you what this my definition is. So as I said, it consists of 3 capabilities. And so the first one is generalization. So it's acquiring beliefs by generalizing from experience. And for this, I will mean exactly what generalization means in AI, machine learning now, which is so successful in achieving what AI achieves now. So this is something which has some proven record of being a behavior which can be imitated by a machine and produce human-like behavior. But the main point is that however enthusiastic we may be about all this, it's not everything. So the question is, can we pinpoint some other capabilities we need? So the second capability is some basic notion of reasoning, but of a very specific kind. So once I've learned all these things from experience, I should be able to chain together the conclusions I reach from these learning behaviors to reach conclusions about particular situations. So if I see a situation, I can call upon some learned response, draw a conclusion, and then draw a second response and a third response as some kind of reasoning based on things which I've learned. And the main point here is it's different from logic because I'm combining things which I've learned from experience and have no absolute guarantees. There's uncertainty. So the third aspect is that we can also acquire beliefs explicitly described to us by others. Very basically, we can be programmed. Someone can give us their theory of quantum mechanics, and we can take it into our brains and execute the formulae. So this is an independent capability, which humans are very good at, and of course in classroom situations, our education system is really based on number 3. So to make all these concrete, we have to say a bit more. So all these things have to be realized in common and in a rich enough environment that it's worth doing. And so all of these 3 aspects have to work on a common, what I call a mind's eye. So this is the idea that we can analyze situations, we can make plans, we can put a few objects in our minds and relate them for the first time. You can make a plan about how you're going to leave this conference at the end of the week. And this is the first time you or anyone else in the world has ever thought about this particular instance. And when you make this plan, you can use any of these 3 methods, your own experience, training together, things you know, and advice people have given you. And then also we're very free with symbolic naming. We can give arbitrary names to anything, and this gives us enormous freedom. This is meant to remind one a bit about education, in that there are many educational philosophies. I suppose the third aspect is very much our classical classroom situation. The first aspect is experiential learning, and the second one is applying what you've learned. So these are all aspects of learning which various people say are all very good, and this says, yes, you should do them in combination. I suppose then with respect to mathematics, so number 3 is the content, theorem as definitions. Number 1 is like having examples, and number 2 is being able to do problems. And all these are essential aspects of education. But I think a main comment about this is that these are 3 separate notions. One can't formalize them. They have formalisms, which are, so the first one I formalize as pack learning. The second one is what I call robust logic. And the third one is Turing universality, as in his 1936 paper. So separately, they're fairly clean-cut notions, but maybe as with my physics analogies earlier, it's when you combine the 3 that the interactions are a bit mysterious and hard to predict, and that's where there's some richness here. So if one, so it takes a while to figure out all the consequences, which I certainly haven't yet, but just a quick comment on the various directions I've been made to think after I've started this endeavor. So obviously, the upside of being educable is that some components allow us to discover things by experience. Other components allow us to hand to other people what we've learned. And of course, the culture is spread by aspect number 3. Downside of being educable, briefly, is that we have this incredible capability of absorbing information. I've described to you many ways we can absorb information and structure it, but I haven't mentioned any way in which we can check the validity of information or its truth. Okay, and apparently I suspect, an inherent difficulty in that. So when you learn quantum mechanics, you have to trust your instructor that what they've told you are true experiments and aren't deep fake lies. So we are very one-sided in being able to process information which is thrown at us, but not being able to understand its truth. If educability is a real notion, we should be able to measure it in individuals. And in one sentence, an educability test will be something like you walk in, do something for an hour, but you will test it on your ability to absorb information you're given during this hour, and not on what you've known before when you walked in. So the question is, you can ask whether an individual's educability can be improved, and certainly you can only ask this question if you can do the previous one, measure it. I don't know. I have to emphasize that this uniqueness of this educability notion is certainly with respect to other species, not computers. My definitions are all computational, so anything I define, computers would be able to do also. So I'm decomposing this notion of educability this notion into very computational, very concrete computational terms, which are easy to understand and concrete. So in some sense, removing mystery from AI or even human performance, and which makes it less fearsome. And I think that's good. And certainly, although it's not targeted at education, one is left with the question, maybe we can put education on a firmer scientific basis than it is at present. So at present, we know that medicine has a basis in biology, engineering has a basis in many fields, but education isn't so well grounded. So there may be possibilities to improve on that. So thank you.
Thank you, Leslie. As promised, perfectly on time. So because I know we need to move on to the second session, please do come and find Leslie in the coffee break for questions. But if we can do a final round of applause both for Leslie and for all of our speakers this morning. Thank you.